Hello. In this video, we continue with our study of one electron atom in which the orbital quantum number L determines the magnitude of the electron's angular momentum. Now, an electron revolving in an orbit about the nucleus of an atom is a minute current loop, and therefore it produces magnetic field, and it therefore also behaves as a magnetic dipole. Now here we consider an electron in this given figure which is moving with a velocity v in the direction as shown, and it is moving along a circular orbit with radius r. R there shows the position at that instant of time with the direction provided, and we can have the current that is associated with the loop that is equal to I, and that is equal to the charge of the electron over the time period that it takes for one complete cycle. And as we know, for one complete cycle it will be taking a distance of 2 pi r in terms of the magnitude concerned, divided by the speed, and so the speed distance over the speed gives us the time, so we can substitute that over there, so we get the current to be equal to the charge multiplied with the velocity over 2 pi r, that is the circumference. Now, as per the electromagnetic theory, the magnitude of the orbital magnetic dipole moment is mu L, that we have provided over there, for a current I associated is given as I times of A, that is the current multiplied to the area vector, again directed along the direction of that, or the orbital magnetic dipole moment directed along the direction of the area vector. But here we are speaking of the magnitude, so we'll do away with the vectors as of now. So let's not put that vector sign over there. So that gives me the magnitude of the orbital magnetic dipole moment. Now from that, as we know that the area is going to be pi r squared, so we have this value to be also equal to mu L, which is equal to well, we can substitute the value of I, that is E v over 2 pi r, and the value of the area, that is pi r squared. So one of the r gets cancelled, the pi's get cancelled, and so we simply have EVR over 2. And because the electron is negatively charged, its magnetic dipole moment will be directed opposite. So now we bring in the vector, so mu L will be directed opposite to that of the direction of the angular momentum. L, as we know, is equal to mvr, and so here also we'll consider the magnitude as of now, and so we have the ratio of the magnitude of the orbital magnetic dipole moment to the angular momentum to be equal to EVR over 2 divided by mvr. So the v and the r get cancelled out, and so that is equal to E over 2m. The ratio of the magnitude of the of mu L, that is the orbital magnetic dipole moment, to that of the magnitude of the orbital angular momentum for the electron is always a constant, because as you can see, the charge of the electron divided by the mass of the electron, they are constant. The 2 factor that is there, that is also constant. This constant that we have is what we call as the gyromagnetic ratio. The gyromagnetic ratio for the electron. And now vectorially we can have, since E is negative, so we have mu L to be directed exactly opposite to that of the angular momentum, as has been shown in the figure at the top. So if we include a constant factor over there, we usually denote this as a negative of GL times of E over 2m L vector, as GL over here obviously is equal to 1. The GL that we have here is termed as the orbital G factor, and it is introduced here to preserve the symmetry with further equations involving G factors which are different from the value of 1. Now, as we know, for L we have that value to be equal to L times of L plus 1, that is the quantum number, orbital quantum number, h bar, or h over 2 pi. So this expression above, we can have mu L, the magnitude that is, to be equal to L times of L plus 1 under root times of E over 2m multiplied to h over 2 pi, so EH over 4 pi m. Now this factor, that is EH over 4 pi m, is a constant unit, and it is a natural unit for the measurement of the atomic magnetic dipole moments, and this is what we call as the Bohr magneton, usually denoted with mu b, Bohr magneton. So its value, well, because these are constant values that we have, so its value can be calculated out. We put the value of E, we plug in the value of Planck's constant, 4 pi, mass of the electron, all of that. Having substituted, we get 9.27 times of 10 raised to the power minus 24, and the unit being ampere meter squared. So what we get for mu L is simply equal to L times of L plus 1 under root times of mu B, and also vectorially we can write the equation finally as mu L vector is equal to minus GL, considering this equation, minus GL multiplied to 2 pi times of the Bohr magneton over h times of the angular momentum. Now we shall discuss about the behavior of the magnetic dipole in the presence of an external magnetic field. As we know that the electron moving along the circular path about a nucleus, for the one electron atom that we are considering right now, in that case it behaves as a magnetic dipole, and there will be a certain magnetic field, if there will be a certain magnetic field which will be acting, the external field that will be acting will cause a certain amount of change in that dipole. Especially what we have learned is that it will apply a certain torque to it, and what happens thereafter is what we will be observing in that level. So first things first, let's consider a diagram for that. So in this figure what we are observing is that we'll have an electron which is probably moving in that plane, so it's a slanting plane that I've drawn. Let me just rectify it a bit, erase the inner circle. So that's one orbit of the electron, and it's going this way. the electron possesses about a magnetic field which is acting absolutely along the z-axis, that is like this. So this is where the magnetic field is directed, the external magnetic field, that is. And then we know that the electron going in that direction, in that sense, we have already studied that we will have the angular momentum to be acting normal to the plane in which the electron is moving. So the angular momentum is directed along this line. And opposite to the angular momentum will be the orbital dipole moment, which is orbital magnetic dipole moment, which because of the negative sign that we just studied. So this is the value, this is the direction of mu L acting oppositely, and this is L, which is perpendicular to the plane. Now there will be a torque which will act, and that torque will act, that is with this mu L, that is the dipole moment, and cross product with B. And if you do the cross product of dipole moment with the torque or with the magnetic field, tau is simply equal to the dipole moment cross B. We have learned all of this in our segment of magnetism and magnetic effect of current. So in that case, we'll see that this torque will be perpendicular to mu L. Now because mu L is just opposite to L, so we can say that the torque will be also perpendicular to L, and that is going to be somewhere along this line. So this is the direction of the torque that will act. Now with that torque, because it's an external torque, that will bring about a change in the angular momentum, because we know that torque is simply, from Newton's law, is going to be equal to dl over dt. Just as in the case of linear momentum, the external force causes the change in momentum, so does the case of torque acting on any object which is in angular motion causes a change in its angular momentum. The Newton's law in angular form. So as a result of that, there will be a change in dl, and the change will act, vectorially speaking, the change will act along the direction of the torque. And as you can see that the torque is acting perpendicular to the L that is present over there, or perpendicular to mu L that was opposite. So the torque acts along this line. So we'll be drawing a parallel to what we have drawn there at the bottom. So it goes like this. Right. So that's the direction of the torque that acts, and also the direction of the change in the angular momentum. Let me erase that L from there in order to avoid any kind of confusion. We'll have the change in angular momentum, that is dl, along that line, and this is L. We can keep the L over here. Now with that dl, the torque will be acting constantly, and so will be the change that occurs in the angular momentum. And this angular momentum that we see is supposedly at an angle theta with respect to the external magnetic field, and it will try and maintain that angle theta with respect to the magnetic field, and as a result of that, this will trace a conic section or a conic path, although the path that I am drawing has overlapped the title of the title that I have provided to the topic, but still I hope you can guess that it's going to be along that line. So that will be the direction of the angular momentum. It will always, and let me use another ink so as to mark the direction of dl changing at that point. So this is dl changing at that point. That's in red. So all of those changes that we see, that will be occurring, and that will lead to a conic precession of the angular momentum about that magnetic field. And that is what we call as the Larmor precession. And that frequency with which it will be moving or processing about the magnetic field, external field, that is termed as Larmor frequency, and we can actually determine that frequency. So if we consider this vector from B, from the tip of B to L, so that is equal to L sine theta, because at the bottom you have thetas. L cos theta will be along B and L sine theta will be directed towards L, and we'll supposedly it covers a certain angle at a constant angular speed omega. In time dt, the angle that it will take will be equal to omega times of dt. So omega dt is the angle that it will cover or sweep in time dt with a constant angular speed omega. That is the case of the angular momentum. So we have from the Larmor precession, we have omega dt, that is the angle, will be equal to, and from the geometry of it we have the angle to be equal to the arc length over the radius. Now the arc length in this case is dl, because that's the segment that it's going to cover. dl over the radius in this case is obviously L sine theta. So dl over L sine theta is equal to the angle, which is omega dt, omega being a constant angular speed with which the angular momentum precesses about the magnetic external magnetic field. Now we know that omega, so therefore will be dl over dt, and that multiplied to 1 over L sine theta. Now dl over dt is simply the torque, which we have already discussed. So the torque over L sine theta, and we also know the value of torque. Torque is equal to mu L cross B. So we can put that over there. So we get mu L B, magnitude wise it will be mu L B sine theta divided by L sine theta. So the sine thetas cancel out and we simply have mu L over L times of B as omega. But as we also know that mu L over L is the gyromagnetic ratio, which is a constant, that is E over 2m, and that is multiplied to B now. So the frequency omega is equal to 2 pi times of the frequency. So the Larmor frequency that we were talking about, 2 pi times of f, is so f here is the Larmor frequency, or the frequency with which the angular momentum precesses about the external magnetic field. So 2 pi times of f is equal to E over 2m times of B, and finally we have f to be equal to E over 4 pi m times of B. And that factor e over 2 pi e over 4 pi m can be also written as mu b, that is the Bohr magneton, uh, over the Planck's constant, that is mu b over h, because eh over 4 pi m would have given us the Bohr magneton. But nevertheless, we'll keep it to that. And it is independent of the orientation angle, that is theta, between the orbit normal and the field, it is B and L, the angle theta that exists. This factor, this frequency, is independent of that angle. No matter what, the frequency is going to be the same. This theorem that we just discussed is of considerable importance in atomic structure, as it enables an easy calculation of energy levels in the presence of an external magnetic field. So keep in mind about this frequency that we just discussed, and the term that we came up with, that is the Larmor precession, an important tool for calculation. And now I've also erased the heading to give you a clearer picture in case you have missed out on that. That is the precession of the angular momentum about the external magnetic field. And also the case will be that the mu L, that is exactly opposite to L, that will also precess about the external field. If extended in the downward direction like that, we'll also have mu L to be precessing about the tail of that B, and in a similar speed, angular speed. But we have already obtained that for the angular momentum, so no point obtaining that for mu L. It will be the same. So that's it from this video. In the upcoming video in this series, we'll be discussing about the spin, the space quantization, and also the electron spin, followed by the Stern-Gerlach experiment, and all of that to follow up and followed by some numericals associated with the topic in the upcoming videos. Till then, thank you for watching.